All right, let's dive into master equations today.
Sounds good.
You might be looking at this chapter called Introduction to Master Equations, and I think
Yeah.
it's a little,
It can be pretty dense.
yeah, it's a little dense,
A
but
lot of math in there.
yeah, there's a lot of math.
But there's some really cool stuff in there, too.
There is some cool stuff. We're going to talk about applications from radioactive decay to the spread of diseases and even things like predator-prey dynamics.
All sorts of things, yeah.
Yeah.
It's amazing what you can model with master equations.
So to start off, maybe you could give us just a general overview of what a master equation is.
Well, you can think of a master equation as a way of describing how probabilities change over time.
Okay.
And in particular, we're interested in systems where you have these jumps between different
Jumps.
states. Jumps, yeah. So think of it like a board game,
Okay.
where every time you roll the dice, you're jumping to a different square on the board.
Okay.
And a master equation would tell you the probability of being on any particular square at any given time.
Interesting. So how does that idea of jumps apply to something like radioactive decay?
Well, in that case, you can think of the atom as being in one of two states. Either it's undecayed or it's decayed.
Okay.
And the jump is the actual process of decaying.
Okay.
And the master equation would tell you the probability of the atom being in either of those states at any given time.
So like the probability of landing on that decayed square.
Exactly.
Gotcha.
And what's interesting is that these jumps don't have to be just one way.
Okay.
So, for example, if you think about someone with the flu,
Right.
they can jump back and forth between being healthy and being sick.
That's true. So we could even apply this to something like someone who's bilingual.
Exactly.
They're jumping back and forth between languages.
Yeah, they're jumping between different linguistic states.
That's a really cool way to look at it.
It's a very versatile framework.
Yes, and the chapter also mentions these two different perspectives, the particle viewpoint and then the occupation number viewpoint.
Right.
What's the difference between those two?
So the particle viewpoint is where you're focusing on the probability of a single particle being in a certain state.
Okay.
So, like, what's the probability that you are sick on any given day?
Okay.
Whereas the occupation number viewpoint,
Yeah.
you're looking at the probability of having a certain number of particles in each state.
Okay.
So, for example, with the flu,
Yeah.
instead of asking what's the probability that you're sick,
Right.
you might ask what's the probability that there are 100 people in the city who are sick today?
Gotcha. So it becomes more useful when you have these particles that are interacting with each other.
Yeah, exactly.
Okay. Now, I got to be honest, when I was reading through the chapter, it starts to throw a lot of math terms around.
Yeah.
Things like transition rates and probability currents and stationary distributions.
Right, it can get a bit overwhelming.
It can be a bit much.
But the concepts themselves are not that complicated.
Okay, so maybe we can break down a couple of those terms.
Sure.
Let's start with transition rates.
Okay, so a transition rate basically tells you how often those jumps happen.
Okay,
So it's not the probability of jumping, it's how often you're actually making those jump.
so in our board game example, how often are you rolling the dice?
Exactly.
Gotcha. And what about probability currents?
So probability currents describe the flow of probability between those states.
Okay.
So if you can imagine visualizing the movement of those particles on our board game.
Right, you can imagine some squares are going to have a lot more traffic than others.
Exactly, and that would be reflected in the probability currents.
Gotcha. And then what was the last one? Stationary distribution?
Right, so the stationary distribution tells you the long-term probabilities of being in each state.
Okay.
So once the system has settled down,
Yeah.
it tells you what the probabilities are going to be.
So after many rounds of the game, what are those most popular spots on the board?
Precisely.
Okay, I think I'm following so far. We've got these systems that jump between states, we've got these rates, and we've got these currents, and eventually things settle down into this stationary distribution.
Right.
But real-world systems, I mean, they're not always that neat and tidy, are they?
No, they're not.
Like, are those transition rates always just these fixed constants?
Well, no, not necessarily. So the chapter talks about the example of chemical reactions.
Okay.
And if you think about, say, sodium and chlorine atoms coming together to form salt,
Right.
the rate at which they react is going to depend on how many atoms of each type are actually present.
Right, yeah, like if there's only one sodium atom and one chlorine atom, it's going to take a while for them to find each other.
Exactly.
Whereas if there are millions of them, bouncing around, they're going to react much faster.
Exactly.
So it's not just, each individual atom making this decision to react or not.
Right.
It's the whole system.
It depends on the state of the whole system.
Yeah.
And that's where the occupation number viewpoint becomes really important.
Okay. Because we have to account for all those interactions.
Exactly.
So this is getting a lot more complex now.
Yeah, but also much more interesting.
It is. It is. So what are some of the ways that we can actually, now that we've started to account for these more complex interactions, what are some of the ways that we can solve these master equations and actually make predictions about how these systems are going to evolve.
Well, one powerful method that's mentioned in the chapter is the generating function method.
Generating function method. Okay.
It can be a bit mathematically
I
involved.
was going to say, is that where the heavy math comes in?
That's where the heavy math comes in, yeah.
Okay.
But it's a very elegant and powerful technique.
Gotcha. And I think there was another one that was mentioned, mean field theory.
Right, so mean field theory is a way of simplifying things.
Okay.
It assumes that the fluctuations in the system are relatively small,
Okay.
so you can focus on the average behavior.
So instead of tracking every single jump, we're kind of smoothing things out and looking at the overall trend.
Exactly.
Okay.
And the chapter gives a really nice example of this with the Lotka-Volterra model.
Oh, yeah, the predator-prey one?
Exactly, which describes how populations of predators and prey interact with each other.
Right, so you get those cycles, like the rabbits will boom, then the foxes will feast, then the rabbits will crash, and then the foxes will suffer.
Precisely.
And then the whole thing repeats.
And you can actually derive those equations that describe those cycles by applying mean field theory to the master equation for the Lotka-Volterra model.
Wow, so we're taking this really complex system with individual foxes and rabbits running around.
Right.
And we're finding a way to kind of zoom out and describe the overall population trends.
Exactly.
That's really neat.
Yeah, it's a very powerful technique.
It is. So it sounds like we've gone from this basic idea of jumps on a board game to understanding how these jumps are influenced by the whole system. And now we're starting to develop these mathematical tools to actually make predictions about how these systems are going to behave.
Exactly.
That's really cool. Now, there's this other equation that the chapter mentions that I wanted to ask you about, the Fokker-Planck equation.
Right.
How does that fit into this whole picture?
So the Fokker-Planck equation is really interesting because it provides a bridge between these jumpy master equations that we've been talking about and descriptions of systems that change more continuously.
Okay.
So remember how we were talking about how those tiny jumps can start to blend together and look like a smooth curve?
Right, like if you zoom out far enough on that board game, the players are just kind of gliding along.
Exactly.
Yeah.
And the Fokker-Planck equation is what lets us describe that.
Okay, so it's almost like we're shifting our perspective
Exactly.
from these individual steps
Right.
to this overall flow of movement.
Exactly.
But you also mentioned Langevin equations earlier.
Yeah.
Are those just a different way of looking at the same thing? Or
So Langevin equations provide a more microscopic description.
Okay.
They describe the forces that are acting on the particle.
Okay.
So you have these deterministic forces like gravity.
Right.
And then you also have these random forces that are coming from things like collisions with other particles.
So it's not just pure randomness. There are these external factors that are pushing and pulling on it.
Exactly. And those random forces are often modeled as what we call OODA,
Okay.
which introduces this element of unpredictability.
Gotcha.
But what's really fascinating is that you can actually derive the Fokker-Planck equation
Okay.
from the corresponding Langevin equation.
Oh, wow. So they're like two sides of the same coin.
Exactly.
Langevin gives us this microscopic view of the forces, and Fokker-Planck describes the macroscopic outcome.
Precisely.
That probability distribution of where the particle is likely to be.
Exactly.
That's amazing.
And this idea of continuous states is something that the chapter doesn't go into too much detail on.
Okay.
But I think it's important to realize that the concept of a state can be much broader than what we've been talking about so far.
Okay.
So, for example, if you think about the temperature of a room,
Okay.
that's constantly changing, right?
Right. It's not jumping between set values.
It's not jumping between set
It's a
values.
continuous variable.
Exactly.
Yeah.
But we can still talk about the probability of the room being at a specific temperature at any given time.
Okay.
And even though temperature itself is continuous,
Yeah.
we can divide its range into tiny intervals.
Okay.
Almost like those squares on our board game.
Gotcha.
And then we can think about the probability of the temperature jumping between those intervals,
Okay.
which is driven by things like heat sources and heat loss.
So we're taking this smooth, continuous variable, and we're imposing this kind of artificial discretization onto it.
Exactly.
But are we losing accuracy by doing that?
Not necessarily, because the smaller we make those intervals, the closer our approximation gets to the true continuous behavior.
So it's like, when you're digitizing an image,
Exactly.
the higher the resolution, the more accurate the representation.
Precisely.
Okay, so we're not fundamentally changing the nature of temperature. We're just finding a way to apply our existing tools to understand it.
Exactly.
And could we use the same approach for other continuous systems, like maybe a particle diffusing through a fluid?
Absolutely. So
Okay.
you can imagine dividing the space that the particle is moving through into those tiny boxes again.
Right.
And then you can use a master equation to describe the probability of it jumping between those boxes,
Gotcha.
taking into account all the forces that are acting on it.
So it's not that the real world is made of these discrete jumps.
Right.
It's that We're being clever about how we use our mathematical tools to
Exactly.
handle this continuous change.
Precisely.
It's almost like we're translating between languages, right? We're finding a way to express the same meaning in a different form.
That's a great way to put it, and it really highlights the ingenuity of these mathematical tools
It does.
and their wide applicability.
Yeah, this whole discussion is making me appreciate the sheer versatility of these master equations.
Yeah.
They can be applied to so many different scenarios.
It's really remarkable.
It almost feels like, more than just equations. They're almost like this universal language for describing change and randomness.
That's a great way to think about it.
Yeah.
And while we've focused on the basics here,
Yeah.
there are more advanced techniques, like the generating function method that we talked about,
Right.
that offer even more analytical power.
So it's like we've learned the alphabet of this language.
Exactly.
And now there's this whole world of literature out there waiting to be explored.
Exactly.
I like that analogy. Well, I'm definitely feeling inspired to delve a little deeper, but I think for now, maybe let's just recap some of the key takeaways from this part of our journey.
Sure.
So we started by talking about these master equations, which describe how systems jump between states.
Right.
And then we started to explore how those jumps can be influenced by the whole system.
Right.
And how those transition rates aren't always constant.
Exactly.
And then we talked about some of the ways that we can solve these equations, like the generating function method and mean field theory.
Right.
And then we got into this really interesting discussion about continuous states.
Right.
And how we can use these master equations to describe systems that are constantly changing.
Exactly.
Like the temperature of a room or a particle diffusing through a fluid.
Exactly.
And we even touched on the connection between Langevin equations and the Fokker-Planck equation.
Right.
It's been a lot to cover, but I think we've laid a really good foundation for understanding these powerful tools.
Yeah, I think so too.
So I'm really excited to continue this discussion in the next part of our deep dive.
Sounds good to me.
And we'll delve into some of the more advanced applications of these equations and explore some of those unanswered questions that are still out there.
I'm looking forward to it.
Me too. So until then, keep those brains buzzing and we'll see you back here soon.
See you then.
So last time, we were starting to talk about continuous changes in systems that don't fit neatly into those distinct boxes. We were just starting to discuss the Fokker-Planck equation.
Right, right.
How does that help us deal with this idea of continuous change?
The Fokker-Planck equation is a way of describing the probability of finding our particle, let's say, at a certain point, even though its movement is based on those underlying jumps.
Okay, so we're shifting perspective from those individual steps to that overall flow.
Yeah, exactly, exactly.
But how do Langevin equations fit into this? You mentioned those last time.
Langevin equations provide a deeper level of detail because they actually describe the forces that are acting on the particle. So we're talking about deterministic forces like gravity, but also random forces like those from collisions with other particles.
So it's not just completely random.
No, not at all.
There are other things that are affecting its movement. Okay, and those random forces are kind of modeled as noise?
Yeah, that's a good way to think about it. And that noise introduces this element of unpredictability, right?
Right.
But the really fascinating thing is that you can actually derive the Fokker-Planck equation from the corresponding Langevin equation.
Oh, wow. So they're kind of two sides of the same coin.
Yeah, that's a great way to put it.
Langevin gives us that microscopic view with all the forces, and then Fokker-Planck is that macroscopic outcome, the probabilities.
Exactly.
That's really neat.
Now, thinking about continuous states, that's something that the chapter doesn't really dive deep into, but I think it's important to realize that this concept of states can be a lot broader than what we've been talking about so far. Like, if you think about the temperature of a room, it's constantly changing, right?
Right. It's not jumping between set values.
Exactly.
It's continuous.
Yeah. But we can still talk about the probability of the room being at a specific temperature at any given time. And even though the temperature itself is continuous, what we can do is divide its range into these tiny little intervals.
Okay, so almost like those squares on our board game.
Exactly, yeah, good analogy. And then we can think about the probability of the temperature jumping between these intervals, driven by things like heat sources and heat loss in the room.
So we're taking something that's smooth and continuous and imposing this kind of artificial discretization onto it.
Right.
Does that mean we're losing accuracy by doing that?
Not necessarily, because the smaller we make those intervals, the closer our approximation gets to the true continuous behavior.
Okay, that makes sense.
It's like when you're digitizing an image, right? The higher the resolution, the more accurate the representation of the original image is.
Right, so we're not really changing the nature of the temperature itself, we're just finding a way to use our existing tools.
Exactly.
Could we use that same approach for other types of continuous systems? Like, let's say, a particle diffusing through a fluid?
Absolutely. You could imagine dividing the space that the particle is moving through into tiny little boxes again,
Okay.
and then use a master equation to describe the probability of it jumping between those boxes, taking into account all the forces that are acting on it.
So it's not that the real world is made of discrete jumps. It's that we're being clever about how we use the mass
Yeah, that's a great way to put it.
to represent that continuous change.
Exactly.
It's like translating between languages. We're finding a way to express the same meaning in a different form.
I love that analogy. Yeah, that's a perfect way to think about it. And it really highlights the ingenuity and broad applicability of these mathematical tools.
It does. I mean, this whole discussion is really making me appreciate just how versatile master equations are,
Yeah.
that we can apply them to so many different scenarios. It almost feels like, I don't know, like more than just equations, almost like a universal language for describing change and randomness.
I like that. That's a really insightful way to think about it. And while we focused on the basics here, remember there are those more advanced techniques like the generating function method that we touched on before.
Right.
And those offer even greater analytical power.
So we've learned the alphabet. Now we're ready for some literature.
Exactly. And those explorations can lead to some incredible discoveries in various fields.
Definitely feeling inspired. But for now, maybe let's recap the key takeaways from this part of our conversation.
Okay, sounds good.
So we started by diving a little deeper into the Fokker-Planck equation, right?
Right.
Understanding how it bridges the gap between discrete jumps and smooth changes in the real world.
Exactly.
We also talked about how Langevin equations give us that microscopic view of the forces involved, which complements that macroscopic perspective of the Fokker-Planck equation.
Right, right.
And I think most importantly, we tackled this challenge of applying master equations to continuous systems, right? We saw how creatively defining our states and using finer-grained intervals allow us to adapt these tools to a much broader range of phenomena.
Exactly. It really speaks to the flexibility and the ingenuity of mathematics, doesn't it?
It does.
But we're not done yet. There are still some fascinating aspects of master equations that we haven't even touched on yet. So join us in part 3 as we wrap up our deep dive and discuss some of the broader implications of these tools and maybe even uncover a few more surprises along the way.
Wow, I have to say this deep dive has really shown me how powerful master equations are.
Yeah.
They're so versatile.
It's amazing how much you can do with them.
Yeah. You know, we started out talking about these jumps on a game board.
Right.
And now we're talking about, all sorts of things, from chemistry to physics to ecology.
It's all connected.
It really is.
The math is the same.
But before we wrap up, I'm kind of curious about the bigger picture.
Okay.
Why are master equations so important?
Well, they give us this framework for understanding how systems evolve over time.
Okay.
It's not just about, predicting whether an atom will decay or where a particle will move.
Right.
It's about understanding the underlying principles of change and randomness.
So it's like a philosophy of change almost.
Yeah, I like
A way of thinking about how things transform and fluctuate.
Exactly. And it gives us this language for describing these changes,
Okay.
whether they're driven by deterministic forces or random events.
Like we've been given a new lens
Exactly.
to view reality through.
It helps us see patterns and connections that we might not have noticed before.
Like what?
Well, for example, you can start to see how things like the spread of a disease
Okay.
and fluctuations in the stock market might actually share similar underlying mathematical principles.
Wow, that's kind of mind-blowing.
It is. It is. It's like realizing that the same musical notes can be arranged to create a lullaby or a rock anthem.
So are there still unanswered questions about master equations?
Oh, absolutely.
Like, where's the research heading?
Well, one area of active research is in developing more efficient and accurate methods for solving these equations.
So even though we've been talking about them as if they're these well-established tools,
Right.
there's still a lot of work being done.
There's always more to learn.
That's exciting.
It is. It's a very dynamic field.
It is. What advice would you give to someone who wants to learn more about master equations?
Don't be intimidated by the math.
Okay.
Start with the basics, build a solid foundation,
Yeah.
and then gradually work your way up to the more advanced concepts.
It's like learning a language.
Exactly.
You got to start with the alphabet.
And most importantly, don't lose sight of the bigger picture,
Okay.
the why behind the equations.
Well, I've definitely learned a lot from this deep dive.
Me too. It's been fun.
It has. And to our listeners, I encourage you to keep exploring these ideas.
There's a whole world out there waiting to be discovered.
And master equations might just be the key
The key to understanding it all.
to unlocking some of its secrets. Until next time, keep those brains buzzing.
And keep diving deep.
We'll see you on the next deep dive.
See you then. ACI 7.